Okay. So my colleagues did a little bit of advertising for this talk. Maurizio and Gary and Paul each mentioned a connection with the Classfile API that I've been working on. So I hope that built a little bit of suspense. So this is something I've been working on with some other folks on the team over the last couple of years. It's been really fun. It's been an interesting process and not necessarily a direct process. So we've been working on this for a while. And about a year and a half ago, we were at the point where we had a functionally complete API. It did all the things that the JVM spec said the class file should support. And I looked at the API and I'm like, I don't like it. I'm not happy. And so people quite reasonably said, okay, what would make you happy? Well, I don't know, but I don't like it. But let's try going in that direction and see if that helps a little bit. And this took a lot of iterations. I probably drove my team crazy. And I was absolutely convinced, correctly, as it turns out, that there was a small, beautiful API struggling to get out of what had started up as a big, sprawling API. So what I'm going to talk about today is not so much the details of the Classfile API, because all of you people know how to read the Java doc and figure out how to use it to do your class file processing. And how many people here have written a program that generates or parses a class file? Everybody in the room, right? Okay. So you all will know how to figure out this API. So what I'm going to talk about instead is the design process and some of the false starts and the design principles underneath it. Okay. So class file processing is, on the one hand, it's this sort of under the hood detail that only geeks pay attention to. On the other hand, it really is quite pervasive through the ecosystem. So there are, of course, tools in the JDK that parse and generate class files, like the compiler. The JLink tool will transform class files on the fly. And the JDK uses class file generation in a lot of places to speed up reflection, to implement Lambda proxies for Lambda forms, for dynamic proxies. And a lot of frameworks in the ecosystem will generate adapters and proxies on the fly just as part of their ordinary doing what they do. And there are probably several dozen class file processing libraries out there in the ecosystem. And in fact, in the JDK, we actually embarrassingly have three. We have a fork of ASM, which is the primary one that we use. There is a special purpose library that's used by the compiler and JDK tools, which we'd like to eventually replace. And there's also a fork of bcell somewhere in a fork of Xerxes or something like that. And so, ideally, that we could be able to get these three down to one. And so my claim is it's long past time for the JDK to provide a class file API. So, okay, let's try to justify that claim. Why are we doing this? Well, one of the things that's interesting about this particular time in history for the JDK is the class file format is evolving quite rapidly. So in the early days, it was fairly stable over quite a large number of versions. But since especially we've gone to the more rapid cadence, more than half of the releases have some impact on the class file format, either new attributes to support features like records or sealed types, or new constant pool forms like constant dynamic, or Valhalla will be bringing us new bytecodes and potentially new type descriptor strings. And even if we don't change the actual syntax of the class file specification, features like private methods and interfaces, which were added in, I think, 9, change the validity checking of a class file of which combinations of flags are valid. So the class file format is under fairly rapid evolution, and I have no reason to think that won't happen. And as the maintainer of a third-party class file API, they might have, I can imagine that they might have some difficulty keeping up. We also use the JDK internally. We use ASM internally in the JDK for a lot of things, like Lambda proxies. And we have this annoying chicken and egg problem where we can't, the version of ASM that supports JDKN can't finalize until JDKN finalizes. So JDKN can't bundle the version that supports JDKN. So at best, it can bundle the version that supports JDKN-1. And that means we can't use some of the new JVM features that were introduced in that version of the JDK in the language translation. We have to wait until the other parts of the JDK that use ASM to parse class files can deal with it. And so, this is something that was, has become increasingly, a source of friction. And so it makes sense to co-evolve the classfile library with the classfile specification. The rapid cadence also makes some trouble for frameworks. So supposing you have a framework that you do some bytecode processing, and so you're going to pick a library like ASM or CGlib or ByteBuddy or whatever your favorite is, and you're going to bundle that with your application. But people might use your framework that was released, say, for JDK 17. They might run it on JDK 20, and that means that it might be presented with JDK 20 class files, and this puts framework developers in kind of a bad choice. Either they have to fail and say, okay, even though I'm running on JDK 20, I can't parse JDK 20 class files, so go recompile your class files for JDK 17. That's not nice. Or they have to cheat and say, well, the class file format probably didn't change that much, so I'll just ignore the version number and keep going, which is what most frameworks probably do. And that's a bad set of choices to put them to. So if they could count on the JDK having a class file library that they can just use, so much the better. So what could we do? Well, we could standardize on ASM. We're not going to do that. And that's not because I don't like ASM. I love ASM. I've been using ASM for 20 years, but it's 20 years old. And it was an amazing thing in 2002. It was the best we could do in 2002. But the compromises that we had to make, or not we, they, Remy, you, compromises Remy had to make 20 years ago are starting to look a little bit stale. And the Java language has improved quite a lot since then. We have lambdas, we have pattern matching, we have seal types. And so we could have, we have more options for designing a good API. So, okay, really? We're going to write a new class file library? Really? We're not going to pick one of the 15 or 20 that are out in the class file, out in the ecosystem? And I know what you're thinking, right? You're thinking, okay, Brian, you've been an architect for 10 years, so that means they probably took away your IDE about 7 years ago, and they don't let you code, and you're just itching to work on a cool library. So you escaped somewhere where you could hack out 20,000 lines of code before the guys in the white coats, came to bring you back to your PowerPoint, right? Okay, guilty. That was part of the motivation, but only a small part of the motivation. But I do have reasons, as in hubris, to believe that we can do better. That not only is co-evolving the library with specification a really valuable thing. But we can design a better API because we have a better language now. And, I've used a lot of these other APIs, and I would say that, they weren't really designed, they just sort of happened. And, because this is something that's so fundamental to the JDK, we were willing to invest what it takes to build a good library on it, even though we weren't quite sure what that looked like at first, but we got there. So, like I said, hubris. So, some of the design goals, took a while to evolve, but since you always get to redefine them at the end, I can claim that we met all of our design goals. We prioritized user ergonomics over almost everything else. So we cared a lot about ease of use, ease of learning, especially consistency, and I'm going to talk about that more. Safety and all of these good things. We deliberately did not prioritize performance. The goal was performance should be good enough, but we're not going to sacrifice ease of use or consistency or readability or or lack of error proneness, just to squeeze out a little bit more performance. And our main tool for getting there was putting all of this on top of a solid functional foundation. So we didn't design it as a functionally inspired library because functional programming is cool, although it is. It's because functionally inspired libraries are successful, and they're successful at meeting that long list of user ergonomics goals that we had. And we took a kind of unusual, but I think wildly successful approach, which was a model-driven design. And we found that was tremendously effective at keeping us honest. And the main lens through which we looked at, are we done or not, was looking at what does the code you have to write to do a class file transformation look like? And in particular, we didn't want to have an API for transformation. We wanted transformation to emerge from the combination of reading and writing and have it compose cleanly. And if it didn't compose cleanly, we weren't done yet. So let's talk a little bit about the domain. It's a messy domain. as everyone in this room has experienced. Classfile looks like a linear thing, right? If you look at the JVMS chapter 4, it looks like a class file is just this linear sequence of bytes, but it's really a tree. So in the class file structure, you have lists of methods and lists of fields and lists of attributes. And in that list of methods, each method has lists of attributes. And one of the attributes in a method is the code attribute, which can have its own attributes in it. And so this really is a tree. And the tree structure is really quite ad hoc, but it is a tree. And when you're reading through a class file, there are many possible ways in which you might want to read through it. You might want to read through it sequentially, processing each field and method at once. You might want to jump around because you're doing some kind of interprocedural analysis and you have to say, okay, now take me back to this method that was like 7 methods ago. You may want to go breadth first because you only care about shallow information like the names and descriptors of methods. You may want to go depth first because you want to examine every bytecode so that you can build control flow graphs and data flow graphs and such. And we don't know how you're going to want to traverse the class file, and we don't want to tell you how to do it. We want you to be able to do it the way that makes sense for your application. So when you're thinking about what an API for this looks like, there's really, I had in mind this 2x3 box where there are 3 basic modes of the things that you want to do with a class file processing API: reading class files, generating class files, and transforming class files. And there's another dimension which you might describe as sequential versus random access. ASM calls it streaming versus tree, where sometimes you just want to walk through the class file and pick out the bits you care about, and sometimes you want to jump around and process certain bits multiple times, et cetera. And if you multiply that out, you could have to design as many as 6 different APIs. We definitely didn't want to do that. But it's actually fairly easy to do that if you're not careful about it. And so we needed some way to prune the design space a little bit. And we had a couple of rough techniques when we started. One was we would like for transformation to be largely an emergent thing, so that which makes our matrix now, instead of 3x2, it's more like 2x2. Okay, that's an improvement. But the most important thing that we did was making sure that we aligned the reading and writing APIs and the sequential and random access APIs to use a common vocabulary to talk about the domain. And this is one of the things that I don't love about ASM, is ASM has a good streaming API and a decent tree API, but you can't use them together because they're completely different APIs. So I knew that I didn't want that, having experienced it and not enjoyed it. So I'm going to walk through a little bit of some code examples from our first prototype, which was sort of where the inspiration came from for, okay, we could do this. So imagine we want to generate bytecode for a method. So here's a simple method, has 2 parameters. It does, if this thing is true, then call the foo method, otherwise call the bar method. So the code for doing this in ASM would look like this. ASM is a visitor-based API, so you get a method visitor, and all of these visit calls are real. You could think of this as an emit call. So we're emitting a method, we're emitting the code attribute. Now we're going to emit a variable instruction and a jump instruction, et cetera. And it's pretty straightforward, but it's not particularly abstract, and there's a lot of details that you have to manage yourself. And we like the builder pattern, but we realized that we could do an interesting twist on the builder pattern to make it more expressive here. So the idiom of builders made sense, but when you have lambdas in a language, you have the opportunity to do some inversion of control. So instead of saying, okay, user, make a builder, and then make a bunch of calls on the builder, you can say, okay, user, hand me a lambda that accepts a builder, and I'll hand it back to you. I'll call that lambda with a builder, and then you do your calls on that. And okay, that sounds really roundabout, right? It's like saying, here, take this piece of paper and give it to me, right? And you're wondering, why am I part of this transaction, right? So it sounds convoluted, but there's a powerful hidden advantage here because it lets the library control the lifecycle of the builder, and therefore we have the opportunity to call your lambda more than once with different code generation parameters. So as an example, how many people here have ever had to write a method splitter because the method got too big, right? Okay, it's a messy problem space, right? And The bytecode instruction set has both short and long jumps, 16 and 32-bit signed offsets. 16 and 17-bit signed offsets, I guess, really. And usually 16 is good enough, so when you're generating a class file, you just generate with short offsets and hope everything works. And asking users to keep track of which to use, unless the user is a compiler for a language like Java or Scala or something like that, it's unrealistic to ask users to do that. So what we do is we give the user a builder that just defaults to all branches are 16 bits. And if one of them overflows, we say, oops. All right, we're going to throw away the method we just generated. We're going to call that lambda again with a different builder, one that uses long offsets. And that way, you can just say, branch this, branch that, say what you want, and we can clean up afterwards. All right, and that's what the inversion of control buys us. So because all the mutation is hidden from the user, the fact that we threw away some generated code and regenerated it is invisible to the user. Okay, so let's take a look at what it looks like with this prototype, our first prototype API. It looks an awful lot like the ASM code. It has almost the same number of lines as the ASM code, and they pretty much map up one-to-one. The builder method names are a little bit more bytecode-y and a little less visitor-y, but that's a pretty small change. It uses, instead of strings, for method descriptors, it uses the Java-lang constant API that we added in JDK 12 because, all right, so how many people here have made the mistake when generating class files of saying foo.bar instead of foo/bar? Okay, keep your hands up. Put your hands down if you've only ever made that mistake once. Put your hands down if you've made that mistake fewer than 100 times. You get my point, right? It's like doing things with strings is incredibly error-prone, and even experts make the same mistakes over and over and over again. So by using a more, a higher-level symbolic API for describing method descriptors and class names and things like that, we can make the client code less error-prone. Of course, if you want to use strings, you can go to the constant pool and say, make me a UTF-8 entry, and you can put whatever garbage in you want. We won't stop you from generating garbage. We'll just make it harder. And the other main difference between this code and the ASM version is just that we do this inversion of control thing, where so we say with code and we hand it a lambda, the lambda accepts a code builder, and then we make a bunch of calls on the code builder. But with this, we can sort of up-level a little bit. So we can offer high-level structuring conveniences that will deal with label generation and branch generation and reachability analysis and control flow. And so there are higher-level builder methods for if-then-else. And what does if-then-else take? It takes two lambdas. What are those lambda takes? Another code builder. And that each of those code builders is specific to the environment in which it's generating it. So so it knows where its start is and where its end is and where its local variables end and all of that. But you can still use all of the, the code generation methods. So that's a little bit cleaner and that's a little bit nicer. And we can do a little bit more with this, right? So if you look at this code, there's a bunch of magic numbers for local variable slots. And another mistake that we've all made hundreds of times, I'm not going to make you admit to your mistakes, but you know who you are, which is everybody. We've all gotten local variable slots wrong with parameters because is there a receiver or not? Are some of them long and double and take up 2 slots or not? So the code builder offers you some help with allowing you to index parameters by parameter number rather than by slot number. And in fact also lets you allocate local variable slots where you say, give me a new local variable slot, and it raises the high water mark. And when you exit that block that you were declared it in, it gets returned to the high water mark, goes back down. So it offers, this idiom offers a lot of conveniences for generating code, more effectively. So there are methods for give me the receiver slot, give me the slot number of parameters 1 and 2, and it lets you do it by parameter number instead. Okay, so that's pretty good. So if I showed you this API and you said, would you rather program in this or ASM? Well, you'd probably say that's pretty nice. I like that. In fact, a lot of people jumped on it, and we have some forks of a prototype of this, still floating around in the JDK somewhere for test cases. It does tick a lot of the ergonomic boxes that we outlined in our in our goals, but only for one of the 6 boxes in that 2 by 3 chart, which is the sequential generation corner of the chart. So on the one hand, working within that little box is pretty nice. The code's, pleasant to use and less error prone and easy to read and all that, and pretty efficient, but it doesn't really scale to the other boxes in our 2x3 chart. So it seems kind of like we're heading down that design 6 APIs while pretending not to be designing 6 APIs route. That was part of what I was unhappy about. The other thing is, there's a lot of ad hoc API surface in this API. There's a lot of what I would call excess creativity, right? So API design is a very creative process, and usually that's a good thing. But you would like for the creativity to be applied at the high level, where you're creative about how you model the thing, and then you're rigidly consistent throughout the API about how you use those abstractions. When you have an API that's sort of as down in the weeds as generating class files, it's very easy to have 17 overloads of every method, and each one of them is slightly different from each one of them because each one of the others, because you looked at it and said, oh, it'd be really nice to have an overload of this that takes this and that and the other thing, and you end up with something that's locally beautiful and globally a mess. So we wanted to use our creativity budget in the right place, and doing it at the leaves of the API was not the right place. So as John is fond of reminding us, the main game that an architect plays or should be playing is the game called Find the Primitive. And the builder API that I just showed you is nice, but it's not a primitive. And so there must be, hopefully there must be, some foundation we can put underneath it that will allow us to have this nice API, but put it on a firmer foundation. And this slide, although it doesn't look like it's all that important, is actually the whole talk. Because it is how we were successful about building this API. And the way we did it, we went about it, was by defining a data model for the class file. And we were very disciplined about only allowing ourselves to be creative in the data modeling. And we were not allowed to use creativity anywhere else in the process. And we were tempted a few times, and we strayed a few times, and every time we were promptly punished when we did. And so the feedback mechanism was really quite direct, that every time we strayed from our principles, bad things happened. So we defined a data model for the Classfile API, and we thought very carefully and iterated several times on how we were going to model the class file. And we defined a meta model where we talked about how are we going to map this data model to a concrete API. And then we forced ourselves to derive the API mechanically, I mean, not mechanically, but without creativity from the model. So it's not surprising that the data model is a big algebraic data type, basically a big tree of sealed types and records. But it does capture everything in the class file and nothing that's not in the class file format. So what does the model look like? Well, I made up a notation and used it in my notebook. That was our process. I didn't use any fancy modeling tools. I picked a notation that was kind of inspired by Haskell's algebraic data type notation, and tried to model everything that was useful about the class file. And in particular, because the class file is a tree, well, for each interesting kind of node, which are classes, methods, fields, and method bodies or code attributes, you have to answer the question, what's in it? So what's in a class? What are the elements of a class? Well, there's a version, there's a superclass, there's a list of interfaces, there are 0 or more attributes, there are 0 or more methods, and there are 0 or more fields. So the model talks about arity with the exclamation marks and the stars and the question marks. It talks about data properties of each of those things. It talks about choices, that these are the elements of a class and nothing else. And similarly, at each level, all right, what attributes can be on a class? Well, it could be a signature attribute or a deprecated attribute, and I just went through the appropriate chapter of the JVM spec, to write this out. And then down at the bottom level, same thing with the code. The element of a method body is either an instruction or a pseudo instruction. The instructions are things like loads and stores and branches, and the pseudo instructions are things like there's a label whose destination is this point in the instruction stream, or at this point in the instruction stream, the line number is 27, right? So obviously the whole model is bigger than one slide, but you've seen all of the modeling, the modeling mechanism that's needed in order to do this. And then we pretty much mechanically turned it into an API. And so for each interesting kind of entity, classes, fields, methods, method bodies, there's an element abstraction. It's class element, method element, field element, etc. There's a sealed type that describes what those are. There is a type which we call compound element, which is an interface that says, this thing is an element of something, but it also has its own elements. So like a method is an element of a class, but it also has its own elements, attributes, etc. And those are the internal nodes of the tree, and then the sort of the leaf elements or the leaf nodes of the tree. And so, and then for each of the interesting types of entities, classes, methods, fields, method bodies, there's a model class. And the model class both gives you sequential iteration, which is let me iterate a stream of the appropriate elements, and it gives you random access of I'm interested in this piece of information now. Give me all the methods of this class. Give me the interfaces of this class. And again, the whole API is, a little bit bigger than this, doesn't fit on a slide, but you've seen all the creativity that's gone into the API design, and we do the same for methods, fields, and code. And then we do the same thing with builders. There's a builder abstraction. Most important thing about the builder abstraction is it's a consumer of the appropriate element type. And so the model is a supplier of the appropriate element type. The builder is a consumer of the appropriate element type, and you can see already how transformation is going to emerge by putting some logic in the middle and diddling with the stream contents as it goes by. And then for each of the for each element in the model, there are builder methods that correspond to with this kind of element, with that kind of element, etc. So I'm making it sound simple because I'm at the end of the process and I'm describing what worked. There were many, many, many false turns before we kind of discovered this. So, okay, so how does it all fit together? Like all the interesting entities, which we call compound elements, we know the user is going to want to treat them either as a single thing or as a source for things, right? So you might just look at a method and say, what's your name? Okay, I'm not interested in you. Then I don't have to look at the method attributes or the method body. Or I might say, oh, I'm interested in that method. Okay, method, explode yourself into a stream of method elements because I'm going to look at those things. And I might do the same thing as I dive into the method body. So for each of these interesting types, there's a model class, an element class, and a builder class whose APIs are derived from the data model. And so if we want to read an entity, we say, give me a stream of your elements. Or if we know I'm only interested in this particular element, we can go directly to a random access method, which also yields the same elements you would have gotten if you had iterated it sequentially. But you can get it in the order you want, and you can get it repeatedly, etc. Similarly, writing a class file is feed a stream of elements to a builder. Transforming a class file is get a stream of elements, transform the stream, and then present the transformed stream to the builder. And the same idioms of exploding, traversing, building, transforming are used at each level, right? And so, through this process, we sort of slowly dug at what the common navigation structure is and made it as common across the different types as possible. So, okay, so let's look at some more code. So ASM does everything with visitors because it's what we had in 2002. But visitors are mostly a hack for languages that don't have pattern matching. And now we have pattern matching, yay. So if I have a code model, which is a method body, and I want to, say, create a list of dependencies for a method, I say, okay, iterate the code model by asking the code model for its elements. And then for each element, I do a pattern switch where I say, oh, okay, are you a field instruction? Okay, let me grab the owning class and convert the name to a string, and I'll put that in a list. And oh, are you an invoke instruction? Okay, I'm going to do the same thing. Are you a cast? Are you an instance of? Okay, do the same thing. So instead of using visitors, we use pattern matching. I think the code is nicer that way. And we use, because we use sealed types here, the IDE will tell you if you type case and then autocomplete, it will tell you what the options are going to be. So that looks kind of nice. Let's go back to our builder prototype and see if we can put a little bit of a foundation underneath it. So the builder prototype had all these ad hoc methods, lots of API surface. Turns out all of those methods are, or in hindsight, were redefined as thin convenience layers around make an element and hand it to the builder. So in our earlier example where it said A-load 0, what does A-load do? All A-load does is say, oh, that's a load instruction for a reference type. So it calls that other builder method. So it's a convenience calling a convenience. What does load instruction do? It says, okay, make a load instruction by calling a factory method and hand it to the builder's accept method. That's all it does. So the example that we saw, which looked like it had a lot of complex surface, those were all just conveniences for making the appropriate objects. Okay, so design principles. The biggest design principle was we wanted all the benefits of a functionally inspired API. So everything is immutable. Everything that's interesting in the class file itself, methods, fields, attributes, annotations, constant pool entries, they're all objects, they're all immutable objects. Navigation is as the user asks for. If you want to explode something into its elements, you ask to do that. If you don't want to explode something into its elements, you can deal with it as an aggregate. So we don't make the user deal with parts of the class file that they don't care about. Similarly, because this is all immutable, we can use laziness under the hood, and we don't inflate objects that the user didn't ask for. We don't even parse parts of the class file that the user is not interested in. So like when we encounter an attribute, all we do is record the offset, the length, and the name of that attribute, and we make a minimal wrapper that describes that, which will fill itself in later if you're interested. And so we do the absolute minimum of parsing to capture the structure of the class file, and everything else is populated lazily. As you might expect, for parts of the class file that are really derived from other parts of the class file, like stack maps and the constant pool and all of that, most of the time that's all out of your face. You can look at it if you want, but you have to ask specifically, otherwise that all the bookkeeping all gets managed by the library. One of the things that I think we achieved here that's an improvement over what other libraries do is that the streaming and materialized views are using the same data model, the same vocabulary, and you can mix and match them freely and without any performance penalty. So you could do some streaming navigation and then say, oh wait, I want this method, the method called X, let me go look that up. And it will, since it's already, if it hasn't already processed the methods, it'll go do that. If it has, you'll just get it out of the cache. And so you can easily mix and match the streaming and materialized views as you like, and everything is lazily inflated. And like I said, the important thing we wanted was that transformation should be an emergent property, and it should be composable. You should be able to define one transform, define another transform, and compose them without having to complex their code. So speaking of transforms, since I said that's really important, what does the transform code look like? Well, there's almost nothing to it. There's a very small API because we achieve this by aligning the reading and writing APIs. So this is sort of design an API by not designing an API. And in fact, we don't even need to use the transform API, although there are reasons to do so. We can just say, get me a class model, iterates its elements, get me a class builder, play those elements into the builder, maybe adjust some of the elements, and we're done. But we can capture this transform of the element stream into an object called a class transform or a method transform or a field transform, et cetera, and that gets us reuse. So I'm going to show you two ways to do the same thing, to give you an idea of how it works. So let's say I want to strip the annotation-related attributes out of a class file. So the way I might do that is say, okay, get me a class file handle, parse the class file into a class model, and now I'm going to build a new class file whose name is the same as the old class file, and then in the lambda that takes a builder, what's it going to do? It's going to iterate the elements of the original class, and it's going to look at each element and say, are you one of the bad attributes? If so, I'm going to do nothing with that. Otherwise, I'm just going to hand that element to the builder. And so what that does is creates a new copy of the class file, except with those attributes removed. And that's really easy, and it's reasonably efficient, but we can do better. So here's another version of the same program where I pull the what am I going to do to the stream of class elements out of into a lambda, which is stateless, and so we can share that and we can reuse it. And the lambda accepts a builder and an element, and the lambda body just does what the lambda body did in the previous example, which is it looks at the element. If it's one of the ones we don't want to keep, we do nothing. If it's one of the ones we do want to keep, we hand it to the builder. And then the transform code is just 2 lines. Parse the original class file into a class model, and then say, now transform it with that transform over there. So that's nicer. But like some of you were thinking that I pulled a trick on you, which I did, which is you can have those annotation attributes not just on classes, but on methods and fields. No problem. We could do the same thing at each level. As we're walking through the class elements, we can say, are you a field? OK, now I'm going to add a field to my new class. And the contents of that field is going to be, OK, I'm going to iterate the elements of this field. I'm going to strip out the ones that I don't like. And I'm just going to I'll hand the rest of them to the builder. And I do the same thing with methods. I say, OK, you're a method. Great. Let's add a method to the class file. Let's iterate the elements of the original methods. Those are method elements. Look to see if you should drop it. If it's not one you drop, you hand it to the method builder. And OK, that is straightforward enough. But like, there's an awful lot of duplicated code there. So let's do better. So I can play the same trick. I can pull the field transform and the method transform into transform objects, which again are stateless constants that can be reused. And then the transform code looks a little bit cleaner because I can use the transform API for fields and methods. And so you look at what am I doing with the class elements? Well, if it's a field, I transform it according to the field transform. If it's a method, I transform it according to the method transform. If it's anything else, I look at it and say, are you one of the bad attributes? And if so, I drop it. Otherwise, I give it to the builder. But we can do better. And this is the part that took us a long time to get to. So I have the same field and method transforms as I had before. And what is a field transform? It's a transform on a stream of field elements. And a method transform is a transform on a stream of method elements. But my main loop here is looking through class elements. I want to transform on class elements. And what I can do is I can lift the method transform to being a transform on method elements to a transform on class elements with a library routine that is about 5 lines long, which says, OK, class element, are you a field? If so, I'm going to transform you according to this field transform. Otherwise, I'm just going to pass it to the builder. And the same thing with the method transform. And then I can say, all right, take the method element transform, lift it up to a transform on class elements, and then compose it with the field transform. What does composing do? It says, take the output of the element stream of one and make that the input of element stream of the next one. And then we do that again with everything that's left. And we say, are you one of the attributes I should drop? If so, do nothing. Otherwise, hand it to the builder. And then the real program for all of that transform is like 2 lines, which is take the original class file, parse it, transform it with this big composed transform, and we're done. And this was what we were aiming for, which is to be able to make these transforms, these things that are independent, can live separately from your code, be shared, be reused, and be composed cleanly, so that if you want to do A and B and C, you don't have to complete the transformation code for A and B and C. So we could have done the first thing, which is done the transform inline without needing a transform API, and we could have done that. But doing it with the transform API not only gives you composition, but it gives you some optimizations. So the composition is great. We were able to lift things and get reuse, but there's also some performance benefits to doing it that way. So let's talk about performance, and I'll talk fast because I'm running out of time. But the question everyone's asking is, how does it perform? And the answer is, I think it performs really well. So that's a very scientific answer. But you probably don't believe me because you looked at, everything is done with immutable objects, and boy, you're creating a lot of objects there, buddy, right? That can't possibly be fast. And well, we do create a lot of objects, but we make up for it by doing a lot less work elsewhere. And overall, this trade-off works pretty well. So we have a couple of performance tricks I'm going to go through that eliminate a lot of work that we otherwise would have had to do that basically pays for the big cost of using an object for everything. So the biggest trick is what we call constant pool sharing. So most transformations, at least in my experience, of which I've written many, only change small parts of the class file. you're like looking through the class file and you're going to inject a byte, like a logging statement here or there, or you're going to inject a method here, or you're going to delete a method there, or whatever. And for the most part, there are big chunks of the class file that are left unchanged. So we optimized for that case. And so what we do when you're transforming, the default is, and you can override this, take the constant pool from the first original class and just have that be the beginning of the constant pool for your new class. And what that means is all the attributes that have constant pool offsets buried deeply in them, you don't have to parse them, explode them, and rewrite them. You can just bulk copy them, with memcopy. And this saves so much work that it pays for an awful lot of objects. And similarly, we talked about like user-driven navigation. If you're saying, okay, give me the class elements, this method, no, I'm not interested in it, just give it to the builder. We don't have to explode it into its attributes to write it. We just take the whole method body, so the whole method info structure, and just copy those bytes to the output. If you do dive into it, then okay, we may rewrite that method and we have to parse it. And so the result is like a do-nothing transform that examines every bytecode of the class file is faster than ASM. There are some things that are faster, some things that are about as fast, some things that are slower, but like the baseline case of I did very little to this class file is very fast. And it sounds a little bit weird to optimize for the case where you do nothing, except the fact that that's actually what most transforms do, is they do very little. So because most transforms don't need to examine the whole class, we are as lazy as possible about parsing, inflation, and rewriting. So for example, if you process a method and you don't change any of the bytecodes, you look at every one of them, you just pass it through to the builder. You look at every exception, exception handler, you pass through to the builder. We'll do a vectorized comparison of the code arrays and say, oh, the code arrays are the same. I don't need to regenerate stack maps. So we're very lazy about what we generate. And so we do the minimum we need to parse to keep our place in the stream and know where an element is and where the next element starts. And inflation is all incremental and fine-grained and invisible, and you don't see any of it. So the last performance trick is not really a performance trick, but a design trick. And this one turned out to be one of the most important ones, which goes back to the data model, which is being very careful in choosing how we represent various parts of the class file. So for example, you might think it makes sense to represent a method descriptor as a string, ignoring the safety issue I described before. That's actually a terrible choice, because what that means is for every method and field, you have to convert the UTF-8 into a string, and then that gets passed to the builder, and then it has to be converted back into a UTF-8 entry, or maybe you have to have a cache that maps strings back to. That's a lot of needless work that 99% of the time the user didn't ask you to do. So we iterated on the data model design many, many times to eliminate all of the needless take it apart and put it back together work, unless the user actually wanted to operate on the data. So for example, with method names, we represent them as a UTF-8 constant pool entry, because that's a structure we had to inflate anyway, and it has an identity. We don't have to say, like, are you the same UTF-8 as that thing over there, because we know what it is, we know what its offset is. So, and we don't even parse the UTF-8 content. We just record the starting and ending offset, and if you ask for it as a string later, okay, then we'll parse it, turn it into a string. And so in the reading example earlier, there was this like word elocution of like, take the field, get its owner, get its name, get its string value. And some of you were probably thinking, boy, that seems like an awfully circuitous way to get a field name. Well, the reason is I don't want to inflate anything unless you want it. And so you take the field. What's the owner? It's a constant pool entry for a constant class info. Okay, what's the name method do? It says, get me the UTF-8 entry for from the name and type from that. Oh, you want it as a string? Okay, you have to ask for it as a string. If you ask for it as a string, we'll cache it. We won't convert it to a string twice, but we're not going to inflate anything until you ask it for us. And so I remember there was this intense period of refactoring where I started to benchmark and realized, oh my God, we're doing so much copying and transformation of formats. And in this, like the course of a week of refactoring this thing, the performance of like a do-nothing transformation went up by a factor of 4, just by picking the right representation that wasn't going to involve needless copying and inflation. So it goes back to our data modeling trick of everything is derived from the data model, including the performance. So it's a little tricky to characterize, is this faster or slower than ASM or BCell or whatever, because ASM's performance is very predictable. It touches everything in the class file, whether you ask it to or not. And so a do-nothing transform or a take everything apart, put it back together transform have roughly similar performance. In our library, it's much more pay-as-you-go. And so if you're only touching if you don't even descend into the methods or the method bodies, it's much faster than if you do that. If you modify things, you pay for that. But so the basic summary of the performance is we do inflate a lot of objects, but we avoid so much redundant work that it largely comes out to be a trade-off. And the immutability powers all of the ergonomic advantages that we talked about earlier. So, okay, so summarizing, and I'm actually just kind of on time, the lack of having a standardized bytecode library has been an impediment for both JDK and JDK developers, Java developers. So we're going to fix that. We're going to put a standard supported Classfile API into the JDK, and we're going to co-evolve it with the with the class file format. And with that, I am happy to take questions. I guess we could take a couple questions, and then we're on break, right? So, questions. So Remy, you can ask me questions any day. Let's see if anybody else has a question first. And Eamon is next.
Okay, so it's not a question. It's
that's even worse.
No. It's to explain the history. So ASM was not built to be fast. ASM was built to be embedded on small devices.
Yeah.
So ASM was designed to don't allocate anything.
Yeah.
That's all I have to say.
And it was, I really don't want people to think that I think ASM is bad. I love ASM. I've been using it for 20 years. I'm just ready to use something else now.
Yeah. And I think you're
Remy's
right.
probably ready to maintain something else now. Okay. So, Eamon had a question?
It's kind of a lost in the weeds question, but I'm wondering when you were talking about keeping as much of the old constant pool as possible, does that sometimes mean that there are unused entries that you haven't figured out?
Yeah, so the question is, okay, you're retaining constant pool. Most of the time that's pretty good, but maybe it's a little bit wasteful. Maybe you have some dead entries. And in the worst case, if you strip all the methods out, you have a lot of dead entries. So yes, that could happen. And you have a choice. When you create a class file context, you pass it a bunch of options. And one of the options is, I always want a fresh constant pool. And it's going to do more work, but you're going to get a compacted constant pool. And so if you care about compaction and you're willing to spend more CPU cycles to get it, then you ask for that. Otherwise, we trade maybe there's a little bit of waste in the constant pool for the so much work we don't have to do as a result of reusing it. So it's a trade-off, and we pick the default is copy, but you can always select a different. Any other questions? Duncan.
Obviously, the class file format is evolving with each JDK release. And if you're writing a framework, how robust is the API if I build it for, if I'm using the API from Java N, how robust is it going to be with Java N+1 or N+2 or N+3 when I hit a new feature or because if we add to the API to handle that new feature, then that's something my code isn't allowed to know about if I built against N. So how do I build frameworks that run nicely on N and still work with N+3 without having to just do multi-release jars?
Right. Okay. So the question is, well, clearly you're going to extend the class file format. You're going to have to extend the API to handle the new surface. So how do I write a client of this to be future-proof? And it depends a lot on what it is you're trying to accomplish, right? And so I'll give you two extreme examples. Most things fall somewhere in the middle. So let's say you're simply trying to compute a dependency graph. Right, so you only care about like some very small parts of the class file. You care about method invocation, field access, and a few other instructions. What's my super type? What's my, what are my interfaces? And so the fact that there might be new parts of the class file that you don't know about, you can probably make a reasonable judgment of, I'll safely skip those. And I will, like if I see a class element that's not one of the types that I've already seen before, I'll just let that fold into my default clause and do nothing with it. On the other hand, like maybe you're doing something like, the kind of transformation that Gary is doing to take a program and run on GPU, and if you encounter something that you don't recognize, it's probably not very good. Or maybe if you encounter a non-attribute that you don't recognize, you encounter a bytecode you don't recognize, right? At that point, again, you're going to switch over the parts you care about, and the default is going to have to do something, and your default's probably going to want to throw, because you're going to want to say, I found something I don't recognize here. So we kind of dump that problem in the user's lap because the user knows more about what they want from their class file parsing than we do. There's not a one-size-fits-all solution. So you can use this API to be, I don't care about the parts I don't recognize, just show me the parts I do recognize. And that works for a lot of different cases. And then you can like dial to the other extreme of, if I encounter something I don't recognize other than maybe a new class attribute, then I'm going to fail. And that's your choice. Right, so the important thing is you understand how your use case works and how you will be, will be affected by, unknown elements of the class file, and then decide what you're going to do. So that's kind of a non-answer, but I think it kind of has to be a non-answer because there's no one-size-fits-all answer. So, all right, cool. Well, why don't we end it here, and we have a break. So I'll be happy to take questions if you want to find me during the break. And we're half hour.